Hi, my name is Cadet Peter Toth. I'm here with Cadet Alex Roos and Cadet David Sang. We are presenting our SCUDEM project, modeling a cockatoo spinning around a wheel. So this is problem B in SCUDEM 5, 2020. So here is the cockatoo video. It's a bird that's spinning around a bicycle wheel. The bird is attached to the wheel, and he spins starting from the top and loops around. So we began with our assumptions. We assume that the device is physically attached to the wheel, that the slider moves forward tangent to the circle, that the center of the mass of the bird remains uniform, that there's friction between the wheel and the axle, that gravity is uniform, no outside force interacts with the model, so it's a closed system, that there are 36 spokes, that torque due to friction is constant, and that the device only extends and retracts with the slider one time.
So looking at our model, we chose for our independent variable time in seconds and our dependent variable to be theta as angular position in radians. And we also created a graph showing the position in x in meters and the position in y in meters. The parameters that we chose to set, we took the constant of gravity, we just chose a radius for the wheel, our radius of the device, we included a unit step function to model when the head would move out, when the slider would move out for the first half of the rotation. We have the mass of the device that we just chose. We also chose the moment of inertia. We found the moment of inertia for the spokes and the moment of inertia for the tire. And then we included a number for the spokes. And then TB represents our torque on the bearing due to friction. So here at the bottom, you can see our final model. We have acceleration due to what we derived from our torque due to the mass, and then over our moment of inertia using physics equations. And then we have acceleration due to friction, and then we can see that we plugged it into a numerical solver to show from a system of equations of angular velocity in relationship to angular acceleration, and then angular position in relationship to angular velocity.
All right, so this is our kind of fundamental concept of design that we were thinking. So here you can see you've got kind of an interpretation of the bicycle wheel with a device attached. So you have two kind of rectangles. This outer rectangle is going to be a device that's permanently fixed on that position on the wheel, so it's going to rotate as if it was part of the wheel. And then you have a slider built in right there, and that's able to move up, down, left, and right. So we created an equation for angular acceleration based on position. That's what Cadet Sang previously touched on. We created a system of differential equations, once again, what Sang touched on. And then we used a numerical solver in order to generate a solution in relation to time. So this is what it ended up looking like. I just gave us interpolating functions. We put them directly into a graph. So the first graph we have is a graph of theta and omega. So that's going to be position and angular velocity over time. So you can see slow start, and then you start to get this almost constant increase in angular position. Obviously, it's going to vary depending on where it is relative to the wheel. And then it's going to slow down slightly as you start to see that acceleration due to friction taking effect. And then this bottom graph here, this bottom line, that's going to be the angular velocity, omega. And that's just going to be, right, this is where you hit the bottom of the wheel, then top of the wheel, bottom of the wheel, top of the wheel, bottom of the wheel, keep going. So then using r sine theta and r cosine theta as kind of like our interpreter, we translated that over to x and y. So you can see when x is maximized, y hits 0, and when y is maximized, x hits 0. So you have like a almost uniform circular motion, except this is non-uniform. Then lastly, what we did was use a parametric plot. So you have your x position here, your y position here, and your time on the z-axis. And so you can see here, you have a slow initial start. And then almost imagine you have like the wheel here, and as the wheel moves forward through time, you can see the position of the device relative to that wheel. So here's a visual representation of the motion. So you can see slow start, back up to the top. As such, just imagine the device being right at the leading edge of that orange slider.
So next we move on to our addressing some of the questions. So first off, does the motion of the object have to change as the wheel's angular velocity changes? So yes, it does. During the first rotation, what happens is the slider extends away from the device. That increases the radius between the center and that slider. And by doing that, what it does is increases the torque, which allows it to go around its rotation. That only happens during the first rotation. Then that slider contracts, and then it is no longer, the object is no longer changing its motion as the wheel's angular velocity changes. And then the second part here, describe the maximum speed that the wheel can spin. The maximum speed is achieved when the device passes around the bottom of the wheel. So on the graph of theta and omega versus time, you can see that on the first hill, the maximum point on the first hill on that angular velocity is that maximum point is the fastest speed that the wheel can spin on that first rotation.
Looking at some limitations, we chose to keep the device as a point mass because we had no information as far as how to model the slider. We also decided that the slider movement is instantaneous, and we chose that air resistance is negligible. So looking into the future, we can decide to actually model this, actually create a replica, and use a device with a servo to control the head movement. We can also expand the function to better represent the head movement and air resistance due to the shape of the bird, because right now our device is simply just a point mass with no air resistance included. Moving forward, we can try and model that as well. Then we can also try to model the angular velocity that the device needs to slow down the wheel. There are moments where the bird walks backwards to slow the wheel down back to a stop. Our model does not include that, but moving forward, we can try to incorporate that.
All right, and then for acknowledgements, first off, huge shout out to Major Kiser. He was a big help in just helping us organize, especially the administrative aspect. He gave us, he helped us put together a team, introduced us to this competition. He gave us classrooms to work on. He helped us with getting used to Mathematica, getting comfortable with it, so we were able to do the programming for this assignment. Then we also obviously need to credit Wolfram Research with their Mathematica program. It was super helpful in being able to use a numerical solver to solve our system of differential equations. Without it, we wouldn't have been able to do anything. We also use Mathematica to generate all those visuals that we referenced in a couple of the slides. Then just for reference, here's our Mathematica code. You can see we have all of our parameters listed here. We have a final time setup because the numerical solver needs a kind of a start and end point for the independent variable. Initial angular velocity, initial angle, then we have our actual system, or our initial, our function for angular acceleration. We have our numerical solver here with omega prime of t equals alpha of t and theta prime of t equals omega of t. So then you have all of the functions that actually generated those visuals. That's all we've got. Thank you.
Thank you.
Thank you.